Get this, the global resistor market, it's going to hit like $15 billion by 2027.
Wow, that's huge.
It's wild, right? And it kind of shows just how crucial these tiny little components are, in electronics.
Yeah, definitely. Resistors are everywhere.
They are everywhere, but why though? What makes them so important?
Well, I think the cool thing about resistors is that they're really simple.
Yeah.
They're passive two-terminal components, and they just add electrical resistance to a circuit.
It's got to be pretty essential in all sorts of electronics, I imagine.
Oh, yeah, absolutely. Everything from like basic circuits on a breadboard to super complex systems like in your phone or even spacecraft.
Okay, so we've got resistors everywhere, and they control current. But how do they actually do that? What's the science behind it?
Well, the key is Ohm's law.
Okay, Ohm's law, I've heard of that.
It's like the fundamental relationship between voltage, current, and resistance.
Right.
So basically, the voltage across a resistor, it's directly proportional to the current flowing through it, and the resistance is the constant of proportionality.
Okay, so let me see if I get this. If we increase the resistance, we're basically like lowering the current for a given voltage.
Exactly. Think of it like a garden hose, right?
Okay.
If you squeeze the hose, you increase the resistance.
Less water comes out.
Exactly. Less water flows through. Same with resistors. Higher resistance means less electrical current can flow.
That makes sense. It's like a bottleneck.
Yeah, exactly.
So we've been talking about individual resistors, but I'm guessing it gets more interesting when you start combining them.
Oh, absolutely. That's where the real fun begins.
Okay, let's get into that then. So what happens when we combine them?
Well, the main ways are series and parallel configurations. These let us change the total resistance in a circuit so we can really fine-tune that current flow.
So series versus parallel, what's the difference?
In series, resistors are connected end-to-end, like links in a chain.
Okay.
Total resistance is just the sum of each resistor's resistance.
So simple addition.
Yep, pretty much.
Okay, that's series. What about parallel?
Parallel is a bit different. The resistors are connected side by side, so the current has multiple paths to flow through.
Makes sense.
This actually lowers the overall resistance.
Ah, interesting.
The calculation is a bit more complex. You use reciprocals and stuff.
I vaguely remember those.
But the main point is the total resistance in parallel, it'll always be lower than the smallest resistor's value.
Okay, so series adds up, parallel goes lower. So by strategically using these combinations, we can really dial in the resistance we need.
Exactly. We can fine-tune it for the desired current flow. And that's one of the reasons why resistors are so fundamental. They give us so much control over electrical energy.
So it's not just controlling the current, it's about shaping it too.
Yeah, exactly. It's about getting the right amount of current where it needs to go.
This is fascinating stuff. It seems like there's more to resistors than just blocking current. What about the energy itself? Does it just disappear?
That's a great question. It doesn't disappear, but it's transformed. Resistors convert electrical energy into heat.
Oh, that's right. Things get warm.
Yep. You know how some electronics get warm after you use them a while? That's the resistors doing their job, dissipating energy as heat.
Oh, I see. So there's this thermal aspect we need to consider too. How do engineers make sure resistors don't overheat and melt everything?
Well, each resistor has a power rating, which tells you the maximum power it can handle safely.
Okay, makes sense.
Engineers carefully choose resistors with the right power ratings to prevent them from overheating and make sure the circuit works reliably.
For our viewers who want to learn more about resistors, what are some common ways they're used in the real world?
One of the most common uses is current limiting.
Okay, current limiting.
Like say you have an LED, which is very sensitive to current. Too much current can fry it.
Right.
So we use a resistor to restrict the current flowing through the LED, protecting it from damage.
So it's like a safety net for the LED.
Exactly. Another important application is voltage division.
Voltage division, okay.
By placing resistors in series, we can create specific voltage levels within a circuit, like setting reference voltages, biasing transistors, or even creating simple sensor circuits.
Could you give an example? I'm having trouble picturing that.
Sure, think of a volume knob on a stereo. That knob is connected to a potentiometer, which is a type of variable resistor. By changing the resistance, we change the voltage at a certain point, which then controls the volume.
So the knob is basically adjusting the resistance, which changes the voltage, which changes the volume.
Exactly, that's how it works.
Wow, that's cool. We're manipulating the voltage by manipulating the resistance.
Precisely. And another common application is pull-up or pull-down resistors.
Okay.
These provide a stable default voltage for a circuit when there's no input signal.
Like a default setting.
Kinda, yeah. Like, think of a button on a digital circuit.
Yeah.
When the button isn't pressed, a pull-up resistor keeps the circuit at a high voltage, representing a logic 1. When the button is pressed, it connects the circuit to ground, overriding the resistor and creating a logic 0.
So the pull-up resistor keeps things in a known state until the button changes it.
Exactly. And these are just a few examples. There are many more ways resistors are used.
Wow, it's amazing how versatile they are.
Yeah, they're incredibly versatile and essential to modern electronics.
It's crazy to think we haven't even talked about different types of resistors yet.
Right. Like, you wouldn't believe how many varieties are out there.
Yeah, it's not just one size fits all, I'm guessing.
Definitely not.
Yeah.
It's like saying there's only one kind of screw.
So let's talk types then. What are some common ones we might see?
One of the most common, especially for like general use, is the carbon film resistor.
Carbon film. Okay.
They're pretty cheap to make and they work well for a lot of circuits.
So what's the deal with carbon film? Why is it good for resistance?
Basically, it's a thin layer of carbon on a ceramic base. The resistance depends on how thick the carbon is and what it's made of.
Huh. Interesting.
You can almost think of it like controlling a smudge of pencil lead.
A smudge of pencil lead. That's a good way to put it.
But for more, demanding applications, you need something more precise.
Right. Like if you need super accurate resistance.
Exactly. That's where metal film resistors come in.
Metal film. Oh.
These use a thin layer of metal, usually nickel chromium, on a ceramic base.
Okay, so what's the advantage of metal film over carbon film?
In metal film resistors, they have less noise, tighter tolerances, and they're more stable with temperature changes.
So they're more reliable, more consistent.
Exactly. They're perfect for things like instruments, audio circuits, and high-frequency stuff.
Right, makes sense. So it's about choosing the right tool for the job. But what about when power is a big concern? What if things get really hot?
When you need to handle a lot of power, you usually go for wire-wound resistors.
Wire wound, those sound heavy duty.
They are. They're made by winding a special wire, like nichrome or manganin, around a ceramic core.
Okay, so they're built to take the heat.
Exactly.
Yeah.
Think of things like power supplies, motor controllers, or big audio amplifiers.
Stuff that uses a lot of juice.
Yeah, circuits with high currents, they need resistors that can handle the heat.
So we've gone from precision to power here. But I bet there are even more types of resistors out there.
Oh yeah, tons. There are surface mount resistors, which are tiny for those dense circuit boards.
Right, I've seen those.
And then there are variable resistors, also called potentiometers, where you can actually adjust the resistance.
Like a volume knob.
Exactly, like a volume knob or a dimmer switch. You're directly controlling the resistance and therefore the current.
That's really cool. It makes them interactive.
And then there are even more specialized types. Thermistors, which change resistance with temperature.
Yeah.
Photoresistors, which respond to light.
Wow.
And even resistors specifically for high-frequency applications like radio stuff.
It's amazing how many different kinds there are.
It really is. Each type has its own special characteristics, and they all have their place in electronics.
It's clear that resistors are essential. I mean, there's so much variety, and they're used everywhere.
Absolutely. Understanding the different types and what they do is super important for designing and building good electronics.
It's been pretty awesome learning all about resistors.
Yeah, we've covered a lot of ground today, from like the basics of resistance to all the different types and what they're used for.
And they're a pretty big deal, wouldn't you say? I mean, these tiny components are in just about every electronic device.
Oh, for sure. They're essential.
And we hope you keep exploring. We're AI experts, and it's been a lot of fun sharing this knowledge about resistors with you.
Don't forget to like and subscribe if you enjoyed this episode, and leave us a comment. Tell us what you'd like to learn about next.
We love hearing from you guys. Thanks for watching.
See you next time.